We're now going to turn our attention to limits of multivariable functions. Now, you recall from single variable calculus, when you're talking about the limit of a single variable function, as x gets closer to the location a, the value of the function gets closer to the value L. Now, you can also talk about an epsilon delta definition of a limit. Now, you may not have used the epsilon delta definition in your previous calculus courses, and that's okay. This definition enables us to get a lot of different results going forward that lead us to continuity and differentiability. Now, when you talk about a single variable function, it's really important to remember that when you get closer to a, you can either get closer from the left-hand side of a or from the right-hand side of a. Well, now what we're going to do is extend this to a multivariable function. And to begin with, we will just start with functions of two variables, x and y. But certainly everything that's discussed in this video and beyond could be easily extended to three variables or any finite number of variables. We're going to use this notation. The limit of x and y approaches some location a and b. Remember that this function now takes points from R2 and returns a real number. And what we want to then do is talk about whether or not the limit of such a function exists. When we have a function of two variables, it represents some sort of surface in R3. So this function is defined on some set D, called its domain. And if we are interested in the limit at a certain point, that means we're taking a point AB in this domain, and we're trying to talk about whether or not the function gets closer to this value L. Now, this notation for limit means take any other point x and y in this domain, and as that point x and y gets closer to the location AB that I'm interested in, the value of this function f of x and y gets closer to L. There's an additional complication because we are in R2. Unlike the single variable case where there were only two ways to approach this point, when we are in R2, we actually have infinitely many different ways to approach this point. We could just go in a straight line like this, or we could approach it from some squiggled path, or any path we'd like. And that complicates things tremendously. So there are infinitely many ways to approach this location AB that we're interested in. Now, there is an epsilon delta definition of a limit. It's essentially saying that we can get as close as we'd like to that output value just by getting arbitrarily close to some input point. Now, because there are infinitely many ways to approach a limit point, the evaluation of limits is best done by epsilon delta definition, and it's best done in analysis courses. So we aren't really going to talk about evaluation of limits in this course very much, other than to show you some basic ideas. What you can do is use epsilon delta definitions to prove basic results. So you can talk about some basic limits, and you can talk about some limit laws. And that's what we're going to do here. We're just going to state these important results. If we ever need to evaluate the limit of a constant, then it's simply just the value of that constant. If we ever need to evaluate the limit of just the function x without any y contribution, this will simply be a. And if we ever need to evaluate the limit of a y term only, then this will simply be b. The value of x plays no role here. We can also talk about limit laws. Now, if we've got two functions, f of x and y, and g of x and y, and we know that their limits exist, then the limit of a sum of these two functions, or the difference in these two functions, is simply going to be the sum or difference of their limits. And if you want to think of it, this would be L plus or minus m. The limit of a multiple of some function, this is the multiple of the limit. And you could think of this as C times L. So both of these rules are called the linearity rules. The limit of a product of two functions is going to be the product of the limit of the two functions. Or you could think of it as L times M. So that's the product rule. There's a quotient rule that says the limit of a quotient of two functions is simply going to be the quotient of the limit of the two functions, provided that the bottom limit is not 0. And this will give us L over M, where M can't be 0. And then finally, if we ever need to take the limit of a fractional power of a function of two variables, so M over N, and that's in simplest terms, then this is simply going to be the power of the limit. Now, if this N is even, so we're talking about even roots, fourth roots, square roots, etc., then we need to have the value of L being greater than or equal to 0. There are other things that can be proven, like the squeeze theorem, but for now, this will suffice. Now, the key idea when evaluating a limit is that there are multiple paths that you can follow, and that complicates things. So what we always need to determine is how to actually evaluate this. Now, usually we will talk about specific curves when we're talking about illustrative examples. So that means we could say things like go along the x-axis or the y-axis or follow the curve y equals mx. Some limits are straightforward to evaluate. So for example, if I had the limit of this function 3x squared y plus the square root of xy, the fact that we have these two basic limits, so since the limit of x is going to be equal to 2 in this case, and the limit of y is going to be equal to 8, since both of these exist, that means the limit laws will apply. And because the limit laws apply, we are just going to apply them. We are going to have the limit of x squared times the limit of y here plus the square root of the product here. And when it's all said and done, we'll have a 3 times a 2 squared times 8 plus the square root of 2 times 8. So that's going to give me a 3 times a 4 times an 8 plus the root of 16. Well, this is going to be 96 plus 4, which is 100. There are some multivariable limits that are more complicated. So here's an example of a limit that is a little trickier than the one we dealt with before. This function is our function f of x and y, and this function is undefined at the limit point. The domain of our function here is the set of all points such that x, y can't be 0, 0. That's the only way that this function is going to be undefined. It doesn't matter that our limit point isn't in the domain. Technically, this is what's called a boundary point of our function. So here's where things get a little interesting. The limit laws don't apply. That limit point is not in the domain of the function. The value of the limit in the denominator is 0, so we need another strategy. We're going to try to talk about evaluating paths directly. So let's say we would like to go along the x-axis. So when we are on the x-axis, that means all the y-coordinates are 0. So the function simplifies tremendously. It's going to go x plus 0 squared, x squared plus 0 squared, which just gives us x squared over x squared is equal to 1. And that means whenever we talk about the limit of the function going along the x-axis, we are essentially evaluating the limit of 1. Now be careful, just because this limit exists doesn't mean that the limit of the function exists. All we've done is said, hey look, let's walk this way. But there are still infinitely many different choices that we could make. So for example, let's walk along the y-axis. And when we walk along the y-axis, that means all the x values are 0. And that means the function simplifies down to 0 and y. So once again, we'll have something similar to what we had above. all of the x terms will turn to 0. We'll end up getting a y squared over a y squared, and that equals 1. Remember that x can't be 0 and y can't be 0 because that isn't in the domain of the function. So that means if I ever wanted to take the limit as I approached along the y-axis, guess what? The limit exists and the limit is equal to 1. Hey, does that mean that the limit exists? Nope. The limits are the same for two specific paths. Two specific paths doesn't cover all the possible paths. Let's say we approach along lines that go through the origin. Now, in this particular case, when I substitute this into my function, I'll have x plus y, so x plus mx all squared over x squared mx squared. So I'm just going to do a little bit of algebra. Remember in the top here that I could factor out an x, and all of this is going to get squared. And in the bottom, there'll be a common factor of x squared with an m squared as such. This x squared will cancel with that one, so I'll get a 1 plus m all squared over 1 plus m individually squared. And this now illustrates to us what's happening. If m is equal to -1, that means then that the function is x and negative x. That's going to give me a 0 over 2, which is a 0. In this particular case, the value of the limit is 0. It doesn't match the values of the limit that I got above. And that means then that the limit does not exist. And if you want to think about it graphically, what's happened is now I'm walking along the line y equals -x. And if that's the case, then the value of the function goes to 0. Now, similarly, if m is equal to +1, that means I'm walking along the origin along the line y equals x. And in this particular case, the function will give me 2 squared over 2, which will be 2, and therefore the limit of the function will be a 2. What's happening is that multivariable functions are more complex, and depending on which way you approach the origin and at what height, you can get very different results.